Sorry for the delay. So I'm here to present you the work entitled Design of a STEREOACUITY Holographic Test. So let me first start by extending the difference between apparent depth and real depth. This is fairly important, especially these last few days with all this VR, AR technology. The main difference is something that's actually in 2D, that is not physically apart in the real world. But because of something called monocular clues, we are just able to trick our brain into giving us the cues of what's placed in front of behind, despite the fact that they don't have an actual 3D position in the spatial space. So what is stereopsis? This would be mainly depth perception, but it's the more, let's say, fancy way of putting it. And it's also that related to ocular terminology. It's something that needs three main things. So first of all, binocularity, so having two eyes. Then the fusion, so having those two images received by those two eyes and fusion in the brain. And then binocular disparity. So how to explain binocular disparity and why we can mimic that with some of the tests that we currently have. It's easily explained by, if you can see in the images, the actual difference where the image impacts the retina. From the left to the right eye, that distance is going to change. So if we perceive our retina as a sensor, that pixel distance is different. And as you can see, if we place at a specific distance in a screen so that the perceived image in the retina is that exact same distance, we can trick the brain into thinking that we are seeing, as you can see on the right side image, that that sun and that moon are actually a certain distance, where in fact they are not. So what is a STEREOACUITY? A STEREOACUITY is for us, or other called SVA, the way of measuring this capacity. And the definition is the difference between the angles of 2 points, whether they are in front from a certain plane or behind from that plane. Those 2 points and the angles that they generate when you extend lines from those points all the way to our eyes, that's going to be what we call SVA. So the formulas that we will be using for the SVA calculation are in some way approximate, because we deem that the delta D, or this difference between the angles or the 2 points of the object in depth, are way smaller than the distance D at which the observer is placed from the object. We can just simplify them, and the calculated error to be, even for very great surface values like 800, is below 2.5%. And especially because we aim to go to a very accurate or reduced SVAs, this is proven to not be an issue. So right now, the way on which we generally measure the STEREOACUITY is by the test that almost everybody in the optometry field knows. And they're separated in the different areas, mainly stereograms and real depth. From its own name, real depth is the one where there's some objects actually placed at a certain distance in the real world, and we are just trying to get the patient to tell us whether one object or the other is in front. But they present many issues, especially the Howard-Dolman test, that is considered to be the gold standard, cannot really be used with kids, and it's very bulky and not compact at all. So it's something that limits the ability of having that everywhere for ready to use, like in a hospital environment. On the other hand, stereograms, we have contour and TNO, but both of them, they necessitate of external things like glasses, whether they are red and blue or green or polarized glasses, it doesn't matter. And also we cannot tweak the actual SVA. They are as they come, then you cannot change them. Or if you're uncertain of whether a patient really sees the difference between 50 and 100, there's no 80 in between. So that's an issue. And we wanted to tackle that. So creating a new one, and which better way than by using holograms and therefore holography. And what is holography? So in kind of like just sprinkle the basics of holography are, we are all familiarized with photography. So in photography, we have light intensity, but we don't have the phase information. And why does this phase information is so important? Is because it what dictates and holds the 3D information, and not just the amplitude, the intensity, as photography does. So holography can be broken down in mainly two steps: the recording phase and the reconstruction phase. The recording phase is, well, you actually create the interference pattern by splitting a laser beam that then you're going to shine with one of those two beams in order to obtain the second one. And they will be called respectively reference and reconstructed beam, or object beam, because it's the one that holds the information from the object that we aim to record. Among holography, there's a few different types of holograms. The most common ones, transmission and reflection. In this case, we will just be using reflection ones, so I won't dive into the other ones. But for a slightly further introduction into reflection holograms, the key thing here is that the HOE, as is depicted, the holographic optical element, holds a photopolymer and receives those beams on different sites, and then the reconstruction wave, it will be the reference wave, and therefore obtaining our reconstructed object, not as a perceived something, but as a real object. Okay, so the objectives are clear. We want to develop a new holographic stereoacuity. We want to compare it to the ones that exist and see if it's something that allows us to obtain valuable results. The photopolymer we use is not very important. There's different types of photopolymers out there, with depending on what we want, the wavelength that we want to use, the diffraction efficiency that we want to achieve, the refractive index, modulation. But in this case, we chose this one because it's a readily commercially used one, and because it has the minimum transmittance in for around 433, so close to the green, and green is very very nice on the eyes, because it's out of 3 RGB colors, is the one that is perceived the best. So the recording setup, the recording setup is fairly basic, and you might wondering that we have only one beam, we haven't split it, and I said prior to this that we needed 2 beams, but in this case we are using something that's called Dennis-Duke type of holography. In this case, the same reference wave is going to pass through the transparent photopolymer. It's going to then hit the object. That reflection is going to come on the other side, and that's what's actually holding the object information and acting as our object wave. The object we use, it was just some white 2D image, but because it's placed at a certain distance that we will be moving with the micrometer, we can tweak, and by using the formula that I presented before, set which actual SVA we want to achieve, making this us the limiting factor of how many steps we want to take. We could even take 1 degree steps if we wanted. So the obtained holograms, as presented, and mainly they were done on a flavor of different ones, using the actual stereoacuity that the ones that we use currently use, so 800, 400, and so on. Then we broke that barrier and we went even farther to 40 and 25, so that we could compare with the other ones. This table just shows the calculation on the movement that we had to make in the micrometer in order to place the image at a certain distance that would be then equivalent to the desired SVA. The data gathering was very simple. We just wanted between age 16 and 60 with the best prescription and with no ocular pathology or any accommodation issues. We had 21 patients as sample, and we compared them with Frisbee and Titmus and our holographic test. The sorting test works mainly by placing the recorded objects at a distance d that they were recorded at, and by what the patient is perceiving to be in front of and behind. So choosing which one is more or less, and sorting them out in a way where we can see at which point they failed, and therefore that will be the point that we take as their best or max SVA. So the results initially would seem obvious, as we probably know. Titmus is the best, but I'd argue that even though it shows to be the best, because it's the lowest, it's a test that we all know what to expect, and it doesn't really go farther than 50. So even if you're at 60, 40 or anything, you're gonna be at that kind of like low peak. Then if we compare which ones have the best average and how they compare with our holographic test, we could argue that TNO is the one that behaves closest because we achieve a similar SVA average. But then if we perform the actual correlation between all of the tests, we find that Frisbee is the one that is best correlated with our holographic test, which makes sense because out of them, the other three is the only one that's an actual real depth test, like the holographic one. So the limitations for our test would come from the actual interpupillar distance, because even just a small variation, we're using an average, but among humans it does change, and the perceived error is fairly high, just on a just 5 millimeter is gonna generate an 8.33 error, as well as the distance. Even though patients are asked to not take by hand and move the samples, any variation in the movement from their position is varying that distance from the patient to the sample, and therefore that can induce a very high error, as you can see on the second table. So in conclusion, we would argue that we managed to prove that developing a holographic test in order to measure and possibly use it for therapy vision is possible by using holography, and that the comparison between the other tests proves that they have all of them, the limitations. This would be a much more compact, easy approach, especially for kids. And even though further work could be performed, basically the technology stands that it's something that holds huge promise for the future. So thank you, and if you have any questions, I'll be glad to answer them.